OpenFlow Protocol operates between SDN controller and switches and control devices, that is, in the southbound interface. It operates over TCP with a default port number 6653. There are three different classes of OpenFlow messages: messages from controller to switch, messages from switch to controller, which are also called asynchronous messages, and symmetric messages that can be sent from both the controller and the switch without any solicitation between them. Important controller to switch messages in OpenFlow include configure, modify state, and packet out messages. In configure message, controller either queries or sets the switch configuration as determined by the controller. Using modify state, flow entries within the tables are modified. And using packet out, the controller can send a packet to the switch to be sent out of a specific switch port. This is at the granularity of a single packet and shows the amount of control the SDN controller can have over the devices. Important switch to controller messages are those to report status. Packet in, which transfers a packet to the controller, is used to send a specific packet for monitoring or decision-making purposes up to the controller. Flow removed informs the controller that a specific table entry is no longer available at the switch. And port status informs the controller of a change on a port, helping the controller maintain the status of ports in its view of the network. As you can see, these messages have a high granularity. Maintaining a network by an operator at OpenFlow message level would be impossible. OpenFlow, working with the SDN controller, helps collection of network information and bringing the decided flow tables to the devices. The higher layer abstraction at the controller decides for each of the changes happening at the flow level. For an example of SDN operation, let's consider running a routing algorithm that we already know. This time in the SDN control plane, and compare it to per router control. Suppose we run, as a network controller application, a routing application that uses Dijkstra's link state routing. This will be running in the network control applications and communicating with the SDN controller using northbound interface. So, the communication within the network for link state advertisement will be completely different. Instead of running the algorithm in each router, and routers notifying each other about the link update, the packet switches send updates to the SDN controller. An SDN controller will provide it to the network controller application running the Dijkstra's algorithm. Suppose switch S1 is experiencing link failure. It informs the SDN controller using OpenFlow port status message. SDN controller receives the OpenFlow port status message and updates its link status information. Dijkstra's routing algorithm running in a network controller application has previously registered to be called whenever link status changes. It is called using northbound interface. Dijkstra's routing algorithm running in the application accesses network graph and link state information in the controller and computes new routes. At this point, the network controller application informs the SDN controller about the new decisions. Link state routing application interacts with flow table computation component in SDN controller, which computes new flow tables needed. And at last, SDN controller uses OpenFlow to install new tables in SDN switches that need updating the routes due to the change in the switch S1's port.